I'm going to demonstrate a very simple way of measuring reverberation time in a room. To get a rough idea, of course, you can just clap your hands in the room and listen to estimate the time it takes for the sound to die away completely. Now, for a quantitative measurement, we really need to use a computer. So I've connected up my laptop to a microphone here, and what I can do is to record the sound from the microphone on the laptop, and I'll make an impulsive sound just by bursting a balloon. So I'll start up the computer to record the sound and then burst the balloon, and we can record that. Is recorded onto the laptop. Now, in fact, reverberation is a function of frequency. So in order to get a more detailed analysis, we need to create sounds of varying frequencies. And there's a set of standard frequencies which are normally used. These are either integer fractions or multiples of 1000 hertz. That is 125 hertz, 250, 500, etc. And I've generated tones of these frequencies on this CD recorder here. Now, these signals I've put on here are filtered white noise. So they're narrowband noise signals centered at the standard frequencies. That's 125, 250, etc. hertz. So these sounds stop abruptly, and we can play all the sounds through in sequence and record them onto the laptop and then go away later and analyze them to get the reverberation times at the different frequencies. So I'll just do this now. So here are the noise signals. I'll start up the computer to record these. That was the first one of 125 hertz. The next one is 250 hertz. Then 500 hertz. A 1000 hertz. $2,000. And the last one, 4000 hertz. I'm going to explain now how we can analyze the signals. You can see on the screen I've got the signal which we recorded for the bursting balloon. Well, I've got the cursor, this is where the burst takes place. Now, in front of this and behind we've got a lot of material which we don't actually need, so I'll just delete this and then we'll save the edited file. I could expand that just to show you what it looks like in a bit more detail. So I'll save this as a WAV file onto the desktop. I've opened a program now which will plot the actual levels in terms of decibels. So I'm going to load the file into this. The file, edited file we want was on the desktop, so you see this is how the sound file looks when it's plotted in decibels as a function of time. Now when you look at this, you can see in fact that you can't actually get 60 decibels drop because the sound has dropped into the noise level at the bottom here. But in fact, you can see it drops from about -15 to -45 in, well, about a quarter of a second. So you can extrapolate that directly to say if it falls 30 dB in a quarter of a second, then it'll fall 60 decibels in half a second. So the reverberation time of this room is about half a second. Quite a short reverberation time because it's a very dead room. There are many other ways, more sophisticated ways of measuring reverberation in a room, but the technique I've just shown you here is really about the simplest. In principle, you should have a microphone which is omnidirectional, and also the sound source, instead of just being a combo amp, should really be an isotropic source. But these are really small points which don't make a great deal of difference to the overall result.